Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our second lecture covering material from Chapter 6. We pick up in this lecture right where we left off. We were talking about how we could calculate energy using Planck's constant and the frequency of a wavelength of light, or we could use the Planck's constant times the speed of light over the wavelength. It's important that the wavelength would be in meters for this calculation, and what we end up with is an energy value of joules, which is really joules per just one photon, that one little packet of light. Oftentimes they'll ask for how many joules or maybe kilojoules are in a mole of photons, and we've got an example of this here. And what we do is we use Avogadro's number, and we just apply that as the number of photons in 1 mole of photons. So by multiplying by Avogadro's number, we can get to the mole, and then we can convert from joules to kilojoules. And so you'll want to be able to do this to prepare for an exam. Just something kind of interesting. We talked about trends in the previous lecture and how, like, the frequency, a higher frequency was higher energy, and the wavelength relationship. And we can actually just look at the formula, this energy formula. We got Planck's constant and the frequency. Well, Planck's constant, being a constant, isn't going to change. So if our frequency is large, our energy would be higher. So we can actually use this formula for these trends if we were in that situation. Same thing with the wavelength, using Planck's constant times the speed of light over the wavelength. So we've got two constants on top. If the wavelength got really big, the energy value would actually be smaller. So another thing, down here in the visible spectrum, it's nice to know that the red end of the spectrum, the visible range, is right next to infrared. So we've got red there. And on the other side, the violet end is right next to the ultraviolet. So this kind of helps you keep the visible spectrum straight in relationship to the infrared and ultraviolet. So just a couple little tips there you might find useful. So what we ultimately want to do is figure out what explains why some of these cations are red when they're burned and some of them are yellow. The energy, we know, can vary with a wavelength, but we were just using a propane torch, same setting, and we saw greatly different colors amongst lithium and sodium, for example. And we can start to explain this by thinking about this image where we have like a slope and like a ramp, let's say, and a ball at the bottom of this ramp, a giant ball. And we can push this ball up the side of the ramp, and we have increased potential energy. It's up higher than it was. But if we let go of that ball, it's always going to come back down to what we're going to call the ground state. And this is the lowest energy level, and systems in nature tend to prefer to be at the lowest energy level possible, just like us humans. So this is semi-related to the way an electron might behave. So the Bohr model of the atom, coming from Niels Bohr, might be Niels Bohr, I'm not sure, his idea was that electrons existed in these orbits, and they were circular around the nucleus. And he did a lot of studying of the hydrogen atom, which was brilliant because there's only one electron on the hydrogen atom. So anything he saw must have been due to the one electron. And you can imagine, trying to study a multi-electron element would be much more difficult. So what he found, or what he concluded, I should say, is that we can add energy to an atom, and the electron can be excited to a higher energy level. So we've got these energy levels numbered as n equals 1. That's the ground state in this case. We've only got one electron, and that's the lowest energy level. So that it can be excited to a higher energy level by maybe adding heat from a torch like we did in the demo. And what'll happen is that electron will drop back to the ground state. Now, it might do it in one step or two steps. We're not really sure, but each time it does, when it drops back, it's going to release energy, and that energy may be in the form of visible light. So if we look, I just kind of made up some numbers here and some energy levels, and we said, okay, if we put 100 kilojoules of energy into this atom, this electron could be excited. It would absorb the energy to the n equals 2. It can't go above that with just 100 kilojoules of energy. And as a matter of fact, if we only added 80 kilojoules, it wouldn't even get excited to the next energy level. So we've hit this 100 kilojoules. It absorbs the energy. It's in that excited state. It's in the higher energy level. It doesn't stay there. It goes back to the ground state, and we call this the emission line. And this is going to release 100 kilojoules of energy, and it may just be in the form of light in the visible spectrum. Now, it could be in the infrared. It could be in the ultraviolet as well. But if it's in the visible, we'll be able to see that. Notice, too, how these energy levels are not evenly spaced, and this is correct. So the biggest jump is from n equals 1 to n equals 2. So, but realize that we have to, even though that's the biggest jump, going from 1 to 3 would require more energy than, just going from 1 to 2. Going from 2 to 3 would require only 50 kilojoules of energy, and I just completely made these numbers up just for illustrative purposes. But the big point here is that the steps are not equal, and you'll see that in the diagrams that are given in the text. So in this example, we've got the ground state is n equals 1. We have energy being absorbed, 984 kilojoules. This is enough energy to get to n equals 2. The electron doesn't stay there long. It drops back down, releases that amount of energy. So given off, that's why it has the negative sign. And this may be in the form of visible light. And we could calculate this energy if we had the wavelength or the frequency. This is something that's called a bright line spectrum, and it's kind of like looking at a source of light through a prism that can separate the light into its different wavelengths. So the top one here, the top strip is hydrogen, and I'm just going to focus on this. And there's I can see 4 different lines in that, and I have one circled, and that's a red one. So what that is, what we're seeing is the light emitted when the electron goes from a higher energy level back toward its ground state. It might have went completely to the ground state. It might have went only part way down. So for instance, maybe it was n equals 4. It could have dropped to 3 and released energy that was observed as red light. Now, red light doesn't have as much energy as violet light, right? We learned that before. So there could be some, questions asked, just trying to test your knowledge on the relationship between the visible colors and which has more energy. So I think also this is the reason we saw those different colors. So we're looking at multi-electron species with the lithium and the sodium, but what we're seeing is a culmination of these bright line spectra. So the color we see is, it's a mixture of all these individual lines, and that's why we saw those different colors. It has to do with electrons being excited and then going back to their ground state. This is a type of diagram you might see on an exam, and there's one new thing in here, and it's that very top line, and it says ionization, and it might have a little infinity sign. I've even seen it written as infinity, and what that is that's the amount of energy it takes to make an ion. Well, to make an ion, we have to actually remove the electron. So there is a certain amount of energy that you can provide to drive the electron right off of the atom. So some things here, typical type questions. We have arrows going up. Those are absorption. Arrows going down are emission. And what we need to realize is how energy is related to these. And it can get really tricky because we can then say, well, which absorption line has the highest frequency. Okay, so what we really have on the y-axis here is energy. So we have to realize, okay, which is going to absorb the highest frequency? Well, high frequency is high energy. So we're going to choose a line that represents the highest amount of energy, and that would be A, because that's going from the ground state all the way up, almost up to the ionization state. We can actually calculate potential energy at each of these n levels, and the equations given up above. We have a new constant in here, the Rydberg constant. And notice we have like Rydberg, Planck's, and the speed of light. So oftentimes you'll see these all just multiplied into one number, like one constant. But where that comes from is these three different constants. And this is just over that, what we're calling the principal quantum number. That's the n level. And that's a squared value. So we can calculate potential energy at any of these n's. We can also calculate the energy when we go from one n to another n, and we've got the equation here. And this one also includes Avogadro's number, so we could do this for a mole of photons if that was the case. And so this is derived from the previous equation. We've got our same constants with the Rydberg and Planck's constant, speed of light, and we just have the difference of the final energy level to the initial energy level squared. Really just, equations provided, you just have to punch in the numbers. May or may not need Avogadro's number. So the key thing here is to look for, are they asking for energy per mole, in which case we will have to break that out, but oftentimes that's not necessary. So that's where we ended this lecture, and we're going to start heading in toward some quantum mechanics in the next lecture, and I hope you're finding these useful. So thanks for watching. Give the video a thumbs up and subscribe if you'd like to see some more mini lectures on the Professor's DuBois channel.